extension of this perspective down to the mathematics and logic of interactions, of mechanical interactions. And the basis for modern computer science is very simply the idea that you can have a physical entity, and usually that entity is thought of as potentially being in a number of possible states. This is a kind of notation used to represent a so-called vector. So think of this as a particle. This is particle 1, particle 2, and it can be in one of two states. And computers are, as you know, the kind of computers you use every day, are built up of devices that are so-called bit-based devices, and you can have a whole bunch of them, large numbers of them, nowadays billions and even trillions of them. You can have very large memories composed of these devices that have physical entities that can be, each one of them can be in two states. Modern quantum mechanics, however, allows the following phenomenon. Difficult to appreciate the impact of this at first, where you can have physical entities that look like this. And what this represents is the possibility of having one single entity. These are not two entities. This is one physical entity, but it can actually be in two different states simultaneously. Now, just take that on faith, if you will, for a minute, that such things exist. And what happens is that whereas in a standard computing device, you end up with, you have n of these states. In a device like this, you actually end up with 2 to the n states. At a laboratory in Yale that I was working at for a while, they're building a device that has just 400 of these entities. So in a typical computer that you use, as I said, you might have actually a few billion bits. Building a device at Yale with a mere 400 of these, which sounds like a tiny number, but potentially will end up yielding a memory of 2 to the 400th, which is a number so much larger than the total number of particles there are in the physical universe that it's impossible to convey just how great a number this is. And the people are talking about eventually creating computers with capacities so astoundingly great that it's as close to physical magic as you could imagine. Now, how does such a thing even begin to come into existence, and what does it mean to talk about states being two different states simultaneously at once? Here's the origin of that. And this goes back now to what Feynman originally explained almost 50 years ago. If you have a tank of water and you have a device that just moves up and down and creates waves from two different sources, eventually what you'll end up getting is a so-called interference pattern as the waves intersect. The interference pattern is nothing more than the radiating points of intersection of the waves. This is a very, very well-known phenomenon, and it's easy to calculate the mathematics of where these points of intersection are going to be. If you perform a similar experiment, and instead of having waves, you use particles. For example, you're shooting little tiny atomic bullets out of a gun. and you arrange it like this, first of all, if you have a gun here that's spraying bullets out, individual particles, you have a screen to detect them, and you have this screen is put here in order to ensure that you have just a very narrow beam of particles. You shoot these particles out. Within very narrow limits, you'll always detect the particles appearing at a predetermined spot. If you now make a slightly different experiment, create a screen with two holes, and you put a block on this screen. You have your detector here. Your bullets spray out in all directions originally. This one is blocked. This one is open. Within very narrow limits, you'll detect your bullets coming there. What you expect is that if you have an arrangement where you allow both holes to be open, you have your detector, and bullets are coming out through both places, that you'll have two distinct locations where they're going to hit the screen. But in fact, what has been found, so long as the size of the bullets are small enough, or actually, let me put it more precisely, so long as the size of the bullets and the size of the holes in the screen and their spacing are properly related to one another. That's really all that's required. Technologically, that can be quite difficult to do, but it has in fact been done, and it's been done with relatively large atomic particles, whole atoms in fact. If you arrange your experiment properly, what in fact happens instead is that you find that you will end up detecting these bullets or atoms at regularly spaced intervals all along the screen. In fact, all along the screen, all the way out to infinity in both directions, but that you'll find most of them here, and it will rapidly drop off, going out in both directions. And if you measure these heights, it's the intensity of these heights, the number, the proportion, that follows a so-called wave pattern. That's the origin of the claim that quantum particles are simultaneously waves and particles. Now, what is it that's a wave? Well, first I'm going to answer that question slightly inaccurately, and then I'm going to correct the inaccuracy. But it'll be easier if I answer the question slightly inaccurately first, easier for you to understand it. What is a wave here is the probability distribution along the screen that you will find a particle. So what is being transmitted from here to the detector is a traveling wave of probability. The probability that the particle will be found at a particular location. Now let me correct that. When you measure these heights, you find that the heights don't actually correspond. The mathematics of it doesn't quite exactly correspond to a traveling wave of probability. It corresponds to a traveling wave of the square root of a probability. And in fact, some of the square roots are negative. Now, if you think about it, probabilities in the real world only go between 0 and 1. A probability can be 0. The probability of something happening can be 0. It can be 1 out of 2, 3 out of 4, 4 out of 5, 9 out of 10, or 1. It can't be a negative number. So whatever it is that is propagating through space is something that does not exist in the physical world, but yields results in the physical world. Furthermore, if you perform this experiment in such a way, I'm going to simplify the drawing a little bit, that there's only one particle coming out of here between the time that it leaves the gun and hits the detector. So you've measured how fast it's moving, you've measured the distances, you've turned down the frequency of shooting so low that you're sure that there's only one coming out. In fact, there could be one coming out every week. You still end up with the same probability distribution that looks exactly like the interference pattern that I showed you of two waves interfering. So in other words, what you have are probability waves, or square root of probability waves, that are interfering with each other, even though you have one particle a week coming out. It's worse than that. If you set this up such that you shoot one particle out, you then disassemble the entire experiment, walk away from it, come back a year later, reassemble the experiment, now shoot out a second particle, you end up with the same phenomenon. In other words, this interference pattern will reoccur, will build up over time, the density of particles being located, even though you have disassembled the entire experiment, gone away, and reassembled it once again. Now, there's one other point, and this is the final point about science that I'm going to make, about physics, and that is that even though this probability pattern gets built up with absolutely precise mechanical accuracy, and does so in this astounding way that seems to transcend time and space, but it's perfectly mechanically deterministic. The mathematics of it are absolutely precisely known, so well known that we are now using this phenomenon to build astounding computational devices. And here's the kicker. If you shoot one bullet out, I can tell you with precise mathematical precision exactly what the probability is of where along here the bullet is going to hit. But what I absolutely cannot tell you, and what quantum mechanics says we are absolutely precluded from knowing, quantum mechanics says, in fact, that there is nothing in the physical universe determining it. This is the central point, that there is nothing in the universe determining exactly where it will end up. In other words, the probabilities, the likelihoods, when you look at many millions or thousands and millions of particles, that is precisely mathematically determined. But which particular location any one particle will end up is determined by nothing in the physical universe. And so a number of The back